My name is Harish Krishnan. I'm a member of the organizing committee for this year's conference. And it's my pleasure to introduce the tutorial speakers for this tutorial. So we have three speakers, as you can see. Sergey Wasserkrug is a senior technical staff member at IBM Research, and he's an expert in optimization, game theory, machine learning, with a current focus on LLMs and their applications to OR and MS. And he has his degrees from in computer science and information systems engineering from the Technion. Leonard Bossiou is an assistant professor in information systems and operations management at the University of Washington, Foster School of Business. He has a PhD in OR from MIT, and his research focuses on applying analytics and AI to healthcare, climate sustainability, and societal improvement. And our third tutorial speaker is Wei Sun, who is a senior research scientist at the IBM T.J. Watson Research Center, and her research focuses on the intersection of machine learning and optimization. And she has a PhD from MIT as well. So I will hand it over to the three tutorial speakers. Let's welcome them. Thank you.
Thank you very much. It's a great pleasure to be here. So the tutorial today, as you can see, is about combining large language models and operations research management science for smarter decision making. And I'm here with my two colleagues. I'm Sergey Wasserkrug. So just to get started, just to get to know the audience a little, just one logistical point, we'll be taking questions at the end. So please, let's go through the presentations, and we'll be sure to leave enough time for questions and discussions at the end. So we want to get to know you a little bit before we get started. So what we want to understand is, do you already use generative AI in any sense for operations research management science? We're asking for a show of hands. The first question, who here has used LLMs to assist in their work? Okay, great. And that's really, really nice, because that means almost all of you have tried it out. Second question, have you ever used generative AI tools to develop analytics solutions? Which one of you has? Again, show of hands. Okay, nice, some. Third question, have you created analytics pipelines that integrated large language models as a part of a pipeline or as part of the solution? Again, show of hands. Okay, few. And the final question, who has used the latest O1 model from OpenAI that's supposed to be doing a good job at reasoning? Okay, great, very good. So we'll be talking about that a little. So just to give a little outline of the presentation, we'll be giving a background on the underlying technologies of large language models. We'll talk about how we can already today use generative AI to create better analytics and ORMS solutions. And we'll be talking about three primary use cases. Of course, there could be many more. First would be how to use LLMs in the creations of an analytics solution, using LLM as part of an analytics pipeline, and then how to use LLM as a user interface. And we'll be explaining why this is important. Then towards the end, we'll be talking about some tips, the key takeaways, and we'll be talking about frontiers, where we think or where we believe how the development of generative AI and LLMs can even further help ORMS, and actually also how ORMS can help the development of generative AI. And the key, and the primary learning outcomes that we hope you'll walk out of here with today are that you'll have a much better understanding of the technology underlying large language models. You'll be able to evaluate strategies for integrating large language models to enhance decision-making processes. You'll be able to understand better and to have a sense of how to integrate large language models into analytics pipelines. And finally, and not less important than all the rest, is to identify key considerations, best practices, and emerging trends. Because large language models and generative AI in general, it's a very impressive tool, but it's still just a tool. And so it's very important, we believe, to be able to use it responsibly and correctly. Now, why is this? Why are we here? Why do we think generative AI and language models are so important to focus on? And I think the person who said it very well is Ethan Malik, who's the author of a book called Co-Intelligence, that large language models are general purpose technology, like the internet or like steam power. And so they're good for a multitude of things. They can change a lot of the ways in which people work, and it's hard for us to imagine exactly how they will be used in the future. They're probably going to be used in ways we haven't even thought of. But in contrast to such existing general technologies, like the internet, adoption is extremely rapid. And if you think of the time it took between when the internet was introduced until the time it was used broadly or widely by the general public, it was like decades, right? But ChatGPT, we can see here some figures reached 100 million users in 2 months. And the primary reason is that it's very natural for us to interact and use this tool. We can just do it through natural language. And not only can we do it through natural language, it really has some very, very impressive capabilities, like these abilities to do a better job on even on expert level people in some sense, on tasks or on a variety of tasks that people previously were much better at than AI. And as a result, they could have very impressive economic contributions. Again, you can see some of the figures here, and automate a lot of the workforce. And I want to talk a little bit more about this workforce automation before we move to the next part. And this is also a very important part to understand, because in contrast to previous technologies, for example, like the steam power, right, that sort of removed the more, or helped with the more menial types jobs, here really large language models, we're seeing very strong evidence, can help with very high-end knowledge-based work by experts. These are figures from a study carried out by the Harvard Business School together with Boston Consulting, in which they used business consultants, asked them to create marketing plans, and they showed that consultants who used AI did a much better job than those who did not use generative AI. The quality here, by the way, was measured by people looking at the results and estimating them and evaluating them. But there's another very important point, and that is that AI has what was called in the article a jagged frontier. You can see here, it's not always clear what task is suitable for generative AI and what task is not suitable for generative AI. Another thing they found in the study is that when the same consultants used generative AI for a task for which it was not suitable, they actually did a worse job than the consultants who did, even though it was the same consultants, they have the same skill, they have the same expertise. They would always want the tool to be used to improve and not make work worse. So that's why it's important to understand how to use it correctly and responsibly. And here, I'll turn it over to my colleague, Leonard Bussieux.
Hi everyone, super excited now to dive more into the details of how large language models work. Honestly, it's very complex and it would take multiple lectures to do it. Here, I have 10 minutes to cover the fundamentals. So my goal is to show you some hints and techniques such that you can further your own understanding in your own time. So the first thing to know is that those large language models are no different from other AI models. They learn from data and they use a complex pattern matching to be able to understand text. And what's the key factor of a large language model is the fact that they can calculate the conditional probability of a word appearing next in a sequence based on the context of the preceding words. So if you take the sentence, "the cat sat on the," and you ask the large language model to give you the probability that any word in its associated dictionary can appear. And so it's very improbable that it would be an aardvark. If you don't know what is an aardvark, this is this awkward animal. And the probable answer is more like a mat. The cat can probably sit on the mat. So this is what large language models do. They tell you the probability that every single word can appear next. Thanks to this, you can actually generate sentences. How does it work? If you receive an input, like a prompt, the large language model will pick maybe the most likely next word or sample the word from the output distribution. And then if you have to be or not to be, you want to know what's the next word. So it will be that here. So you take this word that, you feed it back to the initial prompt. So now you have to be or not to be, that, and you ask the large language model to do it again. What is the next most likely word? It is. Now you take is, you feed it back to the initial prompt, and then what's the next likely word? The. And you keep iterating over and over. So this is why we say that large language models just predict the next word, because they just take sequentially what they just generated and feed it back over and over. So some people say that this is why large language models are sort of stochastic parrots. They're very good at repeating what they've seen, and they don't have any intelligence. So it's incredible to think that they can just generate such complicated text just through a simple process like that. However, the training process involved to get there is very complex. So the key factor to understand is that text generation is an autoregressive process. And the model will keep going until it reaches a stopping condition. Like here, for instance, the first paragraph of the soliloquy of Hamlet. So what makes large language models special? 3 things in particular. The first one is that they're based on an architecture called the transformer. This architecture has been invented in 2017. It's using what is called attention mechanisms that allow the model to have a contextual understanding of every single word with respect to the others, and also relate them to all the data that those models have seen during training. And by the way, GPT means generative pre-trained transformer, and because it's based on a transformer architecture. As the name indicates, the second big important thing with large language models is that they're large. They have huge amount of weights. Billions of them, sometimes hundreds of billions. GPT-4 initially was rumored to have more than 1 trillion weights. It's enormous. Of course, if you have that many weights to train, you also need lots of data to be able to fine-tune them and train them using gradient descent. And so you also need these very large training data that are scraped from the internet. All of that combined gives us what we call a foundation model. That's a model that has seen so many things that it becomes good at so many different tasks and can adapt easily. So that's one of the powers of those large language models. The bet that OpenAI made initially was, let's invest lots of money into scaling, because we have some intuition with the scaling laws that more data and bigger architectures will give better performance, and it worked out. So now let's dive more into the exact pipeline of how they work. When you have a text prompt, this is words that we as humans can read, but the AI does not know how to read. It knows how to deal with numbers. This is why we have a process called tokenization. We are going to cut every single word into subwords or units, and every one of them is associated with an ID. So there is a whole vocabulary that the model knows, and it will try to cut all the words into subwords if it does not know this. If the model knows, for instance, Chinese, Korean, Hebrew, it's because every single character from every language also has token IDs associated. That's why the model knows multiple languages, because it has all of those tokens in its vocabulary. Now that you have converted your sequence into a set of numbers, you will do one hot encoding, feed this into the large language model that will give you as an output a probability distribution. So what's the best OR conference? The first choice is, of course, informs. And now we want to decode and give one final answer. There are multiple ways of decoding this, and I'll dive more into this soon. And I'm not inventing it. I actually asked Gemini, ChatGPT, and Claude what's the best OR conference. They all told me informs as their first choice. And then I asked Google, what's the best OR conference? And Google is more like a college football fan. It told me like the best OR conference is the Big Ten and SEC. So you see, like the large language model got my context like out of the blue that I was talking about our field, not about football. So it's fun how different tools can relate. All right, so how do you get those answers? Thanks to the transformer architecture. In this paper, this is what created this huge race towards building more and more architectures. Basically what happens is that now that you have your tokenized prompt, it's going to be embedded by a few layers, and it will go through multiple blocks. Those blocks are just stacked on top of each other. You can have, depending on the size of your model, for instance, from 10 to 100, and in each block you have lots of sub-blocks too. And this is what's going to create sort of this intelligence of the AI, because you're going to process the input over and over. But one key invention that makes those blocks work is called attention mechanisms. There exist so many versions of transformers. There exist encoders, decoders, encoder, decoders. It keeps evolving constantly. It's a super fast field. So here I'm just giving you the foundations, but it's such an active topic in computer science. And why do we need attention mechanisms? If you take two sentences, for instance, the dog chewed the bone because it was hungry, or the dog chewed the bone because it was delicious, you want to know what this it refers to, the dog or the bone. As humans, we immediately understand the context because this adjective does not apply to a bone, or this delicious does not apply to the dog. To be able to understand this, the model needs to pay attention to the different words. This is what attention mechanisms do. They help the model to contextualize all the words in the sequence. So before I explain exactly how they work, I want to give you intuition about 3 very important words for understanding attention mechanisms. So here, this is me looking for information to write an essay about the impact of technology on society. This is what I will call my query, what I want to know. How do I find information to write more about that? I need books to give me that. So I will look for the titles of the books that relate to what I'm interested in. These are the keys, the titles of the books. Now that I figured out which books will help me to write an essay, I actually want to extract the value because I want to read those books. So this is what I will call the value. Query, key, and value are important words for attention mechanisms. So let's see how it works now. Let's say that I have the sentence, I love OR. I will get some input embeddings. Actually, the dimensions are more in the hundreds of values. And then what you want to do with your large language model is to train and learn matrices that are called the query weights, the key weights, and the value weights. Those matrices make the magic of large language models because they are the ones learning how things should relate to each other and help each other. So now that I have those matrices, I just multiply them with my initial input. So I obtain my query, so it means what information I'm looking for. The keys tell me, they tell what you contain. And then now that I know what I search for, what everything contains, I can compute the attention scores, meaning how much attention I should pay to every single input. So like this, you know how much you should focus on every other token in your sequence. And finally, now that you know how to pay attention to things, you will multiply this with the values because this will give you the relevant information for you and represent this initial sentence in an over representation. Large language models do this thousands of times by having many, many layers over and over, because instead of having just 3 matrices, they actually stack so many others. Like this, they can look at the context in so many different ways. That's the power of large language models, and this is what happens when you train them. They learn those matrices. So now going back to here, we now have a beautiful output after doing this over and over, and I do want to know which answer should I select. So I have, for instance, 3 techniques in particular. The easiest one is just greedy decoding. Out of all the tokens that you have, you just take the most probable. Another technique is to select, for instance, 1 token out of the top 2 or top 3 most probable. And then you can resample based on the probabilities. And finally, you can also consider the top tokens whose likelihood will sum up to a different threshold, for instance, 25%. And here again, you will sample from this. There is an important parameter called the temperature. The temperature can rebalance the weights given to each token. So here, for instance, I balance proportionally, but you may want to flatten your distribution or to make it harsher so that you only select what's really probable. This temperature parameter can have a huge impact in creativity or also how reliable your model will be. Great, so now we know how to decode all of this, but if you train large language models on the internet data, they may become racist, sexist, and all the worst thing you can imagine, because it does not know what's aligned with our good human values. So we need one more step. We need to be able to refine the training. And there are just many methods for this. I will only mention two. First of all is to select some demonstration data, domain-specific data that humans have labeled as the one data that you should follow. So you take your large language model trained on a vast amount of data, and you're going to refine it with those specialized tasks, for instance, healthcare data. Other very important technique, you want to give feedback to the answers of the model. So there is, for instance, reinforcement learning with human feedback, constitutional AI, many variations. The way it works is that you have a reward model that tells if you're doing well or not. And then using this reward model, you can just ask the model to give you answers to multiple queries and refine the weights little by little using reinforcement learning. For instance, if you ask which type of optimization model is most suitable for a traveling salesman's problem, the answer might be a linear optimization model. That's an okay answer. You'd rather want something like mixed integer linear optimization model. So I just give a little reward to the model, and I will use this reward to update. They do this in all those big tech companies in so many different variations and flavors. But that's an important concept that the training does not stop about this first stage. There is really some refinement with humans. That's why it's also so powerful and knows so much. Want to mention that there are so many things happening. Sometimes, for instance, to train a model, they actually use a professor model, a teacher model, and they learn from large models to distill them into small ones. So here, this is the diagram from the latest Llama 3.2. You can also adapt the large language models at inference time using the proper prompts. So many techniques about prompt engineering. Just want to mention a few that are very important. One is few-shot prompting. You want to indicate a few examples to your model of how it should behave. Like this, it can imitate that and adapt on the go. Very important also is the chain of thought. You want to ask your model to think step by step, to have a proper reasoning or to simulate a reasoning. And you can include context priming by adding some words like do some excellent answers because the model will relate that to everything excellent it has seen in the training. You can give a model a personality so that it can act like something else. I want to give you a few tips as well. The reason why I love the O1 model is that it enables new use cases that no other state-of-the-art model could do. For instance, if you want to do some copy editing, ask the model to read your whole paper to find any issue before you submit for journal review. No other model was doing this reliably before O1. Of course, you have to be okay to send this into the large language model. So if you have confidential things or you don't want your paper to appear in training data, don't do this. However, I find it to be mind-blowing how O1 is able to catch minuscule little details and really help me. You can ask your model also to check if all the references that are in your main paper are also properly cited in the references and vice versa. So lots of cool use cases with O1 that are very technical. I want to mention that I just covered this super quickly, but I have an entire course I teach at the University of Washington. I open source all the slides, and so we'll share everything, of course, at the end of the talk. And then I will hand back to Segev.
Okay, so now I move to part two, which is how can we use generative AI, or specifically large language models, to help make better decisions together with operations research management science. So, of course, we all know the tremendous, huge benefits operations research management science can bring to enterprise and society. This is taken from the Edelman-Gala book, and this is just these are just the quantifiable benefits. However, and this is one of the reasons why the Edelman Prize is given, is that this requires really a lot of effort, right? It's not something that can be done easily by anyone, because it requires an optimization modeler to set together with a business decision maker, understand the business problem, translate it, and really walk through this very complex process so that an optimization solution can be created for the specific problem at hand and then deployed into the business user's environment. And this also, of course, includes taking into account the multiple stakeholders involved and so on. Now, why is this process so complex? Because, as I said, you need the optimization modeler or the analytics solution modeler needs to understand the decision-making problem, translate it into an appropriate optimization model. And of course, it's not enough just to create a correct model. It has to be tuned for efficiency, right? Because typically real-world problems are very complex and NP hard, and the resulting optimization models are NP hard, so you have to do some work around decomposition, whatever. And only at that point can that model actually be validated by the user, because typically validation is done by looking at the model's solutions and figuring out are the solutions good or not. Then to be run, data has to be gathered and cleansed, and this has to be done. The model has to be deployed, and this has to be done. The whole flow needs to be connected. And perhaps another very important point, two very important points. One is that the model or the outputs need to be trusted, understood and trusted by the human decision maker, right? The mathematical model is typically very hard for the human decision maker to, for the business decision maker to understand. So there needs to be all these mechanisms for the user to be able to trust the model, query the different solutions, play around with them, and so on. Another very important point is that it's not a one-time process, because we live in a very dynamic world, very challenging environment. Things change, new constraints are added, some constraints are removed, and this typically, again, requires the optimization modeler to come back and work together with the business decision maker, which ultimately means that it's very hard to actually have an optimization or analytics solution deployed in real life for a very extended period of time to have any real impact. Many solutions don't even make the deployment stage. Many solutions make the deployment stage, but then don't stay deployed very long, don't stay used very long, and so on. And we believe that large language models and generative AI can help, even today, with these issues. And we're going to talk about how. So the first is how can an analytics solution creator use large language models to accelerate this whole initial process that I showed earlier, going from a business problem to a deployed optimization solution. The second is that a lot of the existing data, and increasing amount, is unstructured data, which requires even additional work, because typically or traditionally it required as a very tailored solution, unstructured data analytics solution to be created and integrated into a pipeline. And what we're going to show here is how we can use a large language model to extract unstructured information without needing to create a model, simply by natural language prompting. And the last is using a large language model, giving the business decision maker an interface, a natural language-based interface, not only to query and understand the model, but often even to do some basic customization, adding constraints and so on for the model, thereby overcoming a lot of these shortcomings or obstacles to creating optimization solutions. And a very important point to emphasize is all of this is done simply by natural language prompting. None of the things that were done here required any fine-tuning or retraining of the models. We used existing models, and simply by natural language prompting show how to provide these capabilities. So the first part is how to use large language models in the creation of optimization solutions. So what we did in order to figure this out, several of my colleagues and I, some which are not here presenting, we took a use case, a real-world business use case, and used ChatGPT to walk through the entire process of creating the solution. And we didn't ask it to create the solution. We used it as a tool for us to show how it could be used to create the solution. And the problem we looked at is the optimization of bike rental hubs. I'm not going to give too many details, just to give you a flavor or the feeling of what was going. So we began by understanding the business, trying to understand, the first step is understanding the business decision problem. Typically, when you go talk to clients or to a customer, they give you a lot of information, some of which about the problem, some of which is relevant, some which is not relevant. So we took this very detailed description and we simply fed it into ChatGPT and asked and said, you're an optimization expert who goes to create optimization solution. This, by the way, shows one prompting techniques, which is role playing. You tell the model what role it should play, and that often results in better outcomes. and the goal is to create an optimization solution. And could you please identify initial problem statements and desired outcomes? And it really ignored a lot of the unnecessary detail and gave a very detailed but much more precise description or possible desired outcomes. This does not mean that these are the exact outcomes, but gives a very comprehensive list of possible desired outcomes. This is one example. The next example is, okay, now we want to understand the stakeholders, and often this requires, when we do when we study operations research, typically we don't know, we study a lot about the math and so on, but we don't really know a lot about the business environment. So often we miss when trying to deploy it, even especially in the more beginning stages of our career, we miss out important stakeholders. So we asked, again, all the list of relevant stakeholders for this problem, and again, it gave us a very comprehensive list tailored to the specific problem. Now, of course, this doesn't mean that these are all the stakeholders. It doesn't mean that every stakeholder in this specific case is equally important, but at least it helps us make sure that we don't miss any important ones. And the final example is, okay, now say we got to the stage where we have a very detailed or very precise natural language description, try to help us create the initial model, and here we gave it and it created an initial model. Actually, it made a mistake in this model. It wasn't a syntactic mistake, it was actually a semantic mistake. It introduced a constraint which was reasonable but does not really exist in the real world problem. But it's a very impressive place to start, right? Or it really accelerates. But what we want to, perhaps the main takeaway that you want you to take away from this using LLMs for this part or for this process is, yes, they can significantly help accelerate the end-to-end solution process. It can also improve the quality, for example, by ensuring all stakeholders are covered, but they do not replace human critical thinking, creativity, and of course not operations research. You use it as a tool because, for example, from the example that I showed here, it's very important to validate the stakeholders. And in this case, it was critical to really understand the business problem and make sure that no mistakes are made so they can accelerate. But critical thinking, expertise, and validation are still extremely important, even though they can help you also become much more proficient in new techniques than previous tools.
All right, so now we are going to cover another type of use cases of large language models, how to integrate them into your data analytics pipeline. So it's one of my big passions. It was one of my PhD specialties about how to reuse very large models to cater to your specific OR problem, for instance. The reason why it's so exciting is that we have so much data available that is unstructured. We have lots of content from text documents, report, customer feedback. There is plethora of images, time series. All of this data is super precious for your pipelines. But integrating them into traditional mechanisms is not necessarily easy because, for instance, machine learning does not really adapt well if it's something outside of tables. So we need to create a translation here. So our goal is to leverage those latest technologies to extract meaningful insights and value from vast amount of data, integrating the unstructured data analysis into your traditional analytics pipelines, and how you can make sure you can maintain consistency and accuracy in the whole process. So I will cover super quick 3 case studies. One is about how you can extract some specific values out of huge amount of data using, for instance, LongChain, which is an open source tool to process lots of data as pipelines. One of my PhD specialties was feature engineering using large models. So I'll show you a little quick study on using multiple feature extractors to understand better different healthcare data. And finally, I will mention retrieval augmented generation, which enables you to enrich the current capabilities of large language models with external databases. So let's dive more into the first use case. Imagine that you scrape text data to analyze a stock market. For instance, NVIDIA is doing very well these days. So now you want to know what's going to happen in the future, and then you have lots of data available, but it's always from different articles. So you manage, thanks to a script, to store everything in a text database. With large language models, you can do lots of things. You can engineer new features. For instance, you can do sentiment analysis, and many apps now propose a sentiment analysis about every stock. You can do some event extraction, so you can, for instance, identify important events, launch of a new product, announcement of results, etc. But also, maybe you can extract information from other analysts. So very often you have papers telling like this group of analysts decided to give this price target. You can extract all this information automatically in an organized structure like a JSON output. There is so many toolboxes to do this. There are no-code tools. There is also open source toolboxes. The principle is you have some mechanisms in Python to handle everything, how to load the data into the pipeline, how to process it, how to store it in the right format, how to extract the insights. In the written version of the tutorial, we have the code, and we also have the tutorial you can follow yourself. But basically, this is also one of the things for the future. We want more than simple AI systems. We want compound AI systems, meaning multiple things interacting together like agent-based. LangChain is such a tool to make it happen. So for instance here, how do you get to extract the forecast data? You may have to declare what model you want to use. You may want to have a text splitter because you have so much text that you need to first create little chunks. Then every single chunk will be processed by some information retrieval system that will look into, do you have information about someone who forecasted the price of my stock? And finally, you can collect the output as a JSON file. So not going too much into the code, but this is available in the written version of the tutorial. Next, case study number 2, feature engineering for healthcare. Imagine you are a doctor and you want to predict if this person needs this drug or needs to go out of the hospital or needs to go to the intensive care unit. Doctors use so much information, time series, images, electrocardiograms, lab tests. We want to bring this data into pipelines to help doctors, but all this data is in so many different formats. So during my PhD with my advisor, Professor Bertsimas, we had a huge effort into making this happen. And then we have used models that are entirely pre-trained, like for instance, the transformers, ChatGPT. We used convolutional neural networks to extract features out of images. We used large language models to understand time series as well. And we used those models to give you embeddings, which mean a vector representation out of your initial data. It means I'm translating an image into a vector. I'm translating a time series into a vector. So I'm basically transforming everything into vectors of numbers. And then I can just concatenate all those vectors together and finally plug those features into a traditional pipeline. That's a super cool use case of those models. Not only can they generate, for instance, text, but they can also extract meaningful representation that summarizes the key features and insights. And really, that was my PhD specialty. Multimodality can have so many significant improvements. It's a really big deal. And there are so many multimodal language models now. Probably if you played with GPT-4 or Claude, you can type a prompt about an image. You can ask also to write text and transform this into an image. You can go from image to video. So many cool use cases. You can have reasoning through multiple images. It all works still with large language models that have the ability to transfer every image into tokens. And then basically now that everything is a token, you can just apply the traditional pipeline. You just need more training data and the ability to transform your initial data into a token format. I want to mention this super cool tool that just came out about a month ago. Everybody's talking about it these days on social media. It's called Notebook LM. If you haven't tried it, go for it. It is generating a podcast out of your video, your PDF. Everybody likes it because it's very fun. And it really generates a podcast that sounds like human-like. They even do jokes. 3 days ago, they released a new version where you can even tune how the host of your podcast will talk. So if you are bored by reading too many papers, feed those papers into this model, ask it to generate a podcast, and next time you're in traffic, just listen to it. So go for trying this tool. Final use case, retrieval augmented generation. The large language models have fixed weights, meaning that if maybe you remember this sentence from ChatGPT, the training stopped in September 2021. How do you get your model to be up to date, knowing you cannot retrain it constantly? By augmenting its capabilities with search abilities. How do you do this? When you write a question, it will be transformed into a retrieval query that will go into a database stored in a proper format. Thanks to this, you collect the relevant information to help you answer the query. You feed it back as information to the model, and it will generate a response containing this extra information on the side. There is a tool that's very popular these days. It's called Perplexity. Here I asked, what is Leonard Boussio's advice to combine large language models and OR MS? The answer is not in any page. It's really a compound of many of the things I've written or talks I've given. The model looked into my website, looked into the last talks I've given, to the abstracts that are online, and finally, look at the answer, multimodal framework. So the model really learned that I love this as one of my key techniques. So you can do new types of searches. It's sort of the baby of ChatGPT and Google. This is how the CEO of this company defines the tool. You can also use it for use cases around how to find the proper papers to cite sometimes. You can, of course, use Google Scholar or Google, but this is a contextualized search. Instead of having to type only 2 or 3 keywords, you type your paragraph for which you want to cite a paper, and the model, because it has all the context, will do lots of queries online, read through many papers, and sort of give you the top results for you. So it's a new way of doing search. Warning, this tool can still hallucinate references, and of course, this is something to be used responsibly. And now I will hand it to Wei.
Hi, everyone. So my portion is about using LLM in a slightly different application. So here we're talking about using LLM as an interface for interacting with backend optimization and other analytical models. As an OR practitioner in the industry for the last decade, what I have observed is that despite decades of training in OR, and we all know that OR tools are very useful, there are still a lot of obstacles when it comes to enterprise adoption of those tools. So one of the challenges come from the fact that in order to implement those tools, you require OR expertise, as well as professionals with background in causal inference, because to answer the question, what is the action to take to drive a certain outcome, the question is inherently causal. So this, to many enterprises, is a very costly and a technical obstacle. And the second challenge, I think we have to be very aware, is that in many scenarios, the decision maker here, they are domain expertise. However, they do not have the necessary technical skills. So here we're referring to pricing analyst for a revenue management application, or a supply chain coordinator for supply chain management. So even if, as an OR practitioner, you have created tools for them, it'll be very hard for them to use. Traditionally, how those AI recommendations have been delivered is through working closely with a group of data scientists who will then present their recommendations in a report, PowerPoint, Tableau, or Jupyter Notebook. However, it will be very hard for domain expertise to generalize these insights and the tools to a slightly different scenario. Think about a new data set, think about having new constraints. Another way to deliver such solution is through purposely build GUI. However, those GUI typically have a very steep learning curve, and they only offer a very static one-way interaction from the end user to the tools. So as we start this project, we were asking ourselves, so now we have the LLM who are able to understand natural language queries. What can we do? Can we use that as an interpreter to understand the natural language query of a backend users and use that to call the backend tools? So those are the optimization models that we can write, we can create. And the whole idea here is we want to make analytical tools more accessible and more impactful for enterprise. So I'm very happy to present one approach from IBM research. So this is our prototype. We call it precise prescriptive causal AI solution for enterprise. So this is an agentic workflow. The intent here is really to help non-OR, non-ML expertise to utilize those tools more effectively. So its backend, it uses a LangChain, which Leo just described about. It's a really nice framework to cascade different LLMs and tools together. While there's no really consensus on definition of a agentic workflow, it can be loosely interpreted as a computer system that's able to achieve certain tasks by interacting with the external environment. So here we're talking about the domain expertise. So this system consists of 4 key components. My next slide, I will have a overall architecture. It will become clearer. So the first, for a agentic, LLM-driven agentic workflow, of course, we need to have LLMs. Different from many applications or examples we've seen earlier, we do not use ChatGPT for this system. So in fact, we made a very conscious effort. We decided that we're going to use open source models for this product. So here I'm talking about the Llama, the Mixtros, and of course, IBM's own Granite series models, because we believe that the transparency, cost efficiency, and the flexibility of the open source model would be really yield long-term benefit for enterprise application. There's one thing that we want to point out, which will be very useful when it comes to LLM applications. So many of the applications we have seen there is, say, you feed to LLM a very large prompt. However, for many applications, enterprise application we deal with, because they are very domain specific, so it uses a lot of the terminology concepts that it's not very common in the general knowledge of LLM. To alleviate that, what you have to do is to create a very, very lengthy, complex prompt to the LLM. But as a result, it may lead to contextual confusion. So the LLM is not able to understand the many different tasks you want it to do. To circumvent the challenge, we actually divide the NLP task, this task of interacting with the backend user, into many specific tasks. So for example, we have one LLM that's responsible for intent identification. So that goal is to parse your input, a domain expertise input, try to map whether this is one of the API calls I can call. And also the LLM responsible for understanding your structured data. When the user uttered a phrase, can this be mapped into one of the features in my column? And of course, LLM for conversation. What makes agentic workflow really powerful is the backend tools. So here in Precise, it consists of several tools, including policy optimization. So learning from observational data, it determines what is a set of optimal action to apply. Causal inference, and also counterfactual reasoning to provide those what-if scenarios. Memory to ensure very consistent conversation flow with the user, and also a reasoning engine. It's primarily used when the LLM understands a query and try to produce an answer. For example, do I need a follow-up? So here is a architecture. As you can see, they are, oops, sorry. My pointer. I can really show it here. Oh, there we go. So we have a different LM responsible for different NLP tasks, as I mentioned earlier. So for example, let's say a user will enter a query like, can you show me the optimal action to take? So this will first go into the LM to parse the intent. Then the reasoning engine will ask a question, can this be mapped to one of my API call, predefined API call, which is one of those tools in the backend? If the answer is yes, the agent will then ask, do I have all the necessary argument to answer this question? So for example, in our optimization model, we will have a budget constraint. We also have the number of rules which define how complex your policy is. We'll then ask if the answer is yes, the agent will then call the backend tools. But if the answer is no, then the agent will first go back to its memory to see whether it can retrieve this information. If yes, call the tool. If not, ask a follow-up question. So in the tutorial that will be online, we included an earlier version of a Precise, which was built built for a airline pricing use case. So during this project, what we realized is that because the application requires a lot of domain-specific term, you had to write really complex prompt. So in the version 2 of the prototype, we decided one of our key improvement for this version is how can we generalize this pipeline. So the user can bring in their own CSV, a very short description of the use case. And then in the back end, what the model will do is to create a prompt database, automatically generate prompt, generate the in-context example for the agent to train on this. I was planning to do a live demo today, but because the Wi-Fi here it's not strong enough, so we provide a live recording of the prototype. So this is a web demo. You go to the website, so you can start. Answer some questions. Hello. So say, hey, I'm Precise. I'm your assistant. I'm here to help you with telemarketing campaign. So this is the use case that we loaded with a UCI data set. So you can ask question, what is our current conversion? So what it does in the back end is actually to look at your CSV and compute what is the average conversion, and also show you a histogram of a historical policy. So what we are seeing is that the 20% of the customer I'm not calling, and I'm calling, for 30% of the customer, I'm calling at most twice. And then the next, the user can ask, what is the AI-generated policy? So here in the back end is actually trying to map into an optimization model. What you realize that the agent realized, I need additional information in order to call this function. So the agent asks a follow-up question. So can you tell me what is number of rules and what is the budget? And the user can continue to have a conversation. He'll ask, what are a number of rules? So once the information is provided and it's running a Cplex at the back end and it produces the result. So now the conversion we see is 28%. Remember the baseline is only 8%. And you can also ask follow-up questions. So for example, in this case, you can ask the model to re-optimize by providing a different scenarios. So we're seeing that now you see it's a more complex policy that is described in the prescriptive tree. So we have several papers around prescriptive trees, which is providing interpretable policy using observational data. So you can also ask questions, can you tell me more about the data set? So this is one of those function calls that does not require an API call, simply based on the system prompt, and the conversation LLM is able to provide a response. There are some other functionality. For example, this is the query that will allow the model to find out the important causal features. So here, it would take some time. But what you will realize, it will also produce a interactive plot. So this is one thing that we want to improvement from version 1 to version 2 is that we want to create a kind of give it a notebook feel. But instead of using Python, can we use a natural language to create a notebook to allow end user to interact with the system? So you can also ask causal related questions. So for example, in this query, we are doing the average treatment effect. So you can see the change in the conversion as a function of a number of calls you made to a user. So what we see is that initially the treatment effect is increasing, but once you start calling 15 times, then the conversion starts to decrease, probably because the user gets really frustrated by the marketing effort. And now you can ask some additional a covariance. So this is what we call the conditional treatment effect given on a particular segment. And of course, you can still query things like, can you talk to me like a pirate? So the response was, matey, while I certainly understand and respond to your request, I must stay focused on our main task. So this is an earlier concept we talked about, alignment. You want the LLM to answer the question, but you do also want to set the constraints so that it still behave responsibly as an agent for enterprise. With that, I'm going to pass the mic back to Leo.
All right, so as you can see, there are so many opportunities for us to contribute with the OR and management science field, because to build such systems, there are so many compounds to implement. So I just want to finalize with a few tips, and Segev will give you also some takeaways. One quick thing, this is not an AI-generated picture. Sometimes we have beautiful rainbow, and I hope some of you saw the one we had yesterday in Seattle. We do have good weather here. So quick thing about ChatGPT 01, I highly encourage you to try it, because this model operates a bit differently. What's different compared to the others is that it can also sort of think during the inference stage. The model is now having a lot of powerful pre-training, but during inference, the model is going to iterate with a chain of thought, so it's going to think and sort of talk to itself. This is not visible to you because OpenAI wants to keep it for themselves. So the model is basically going to autocorrect if needed, and then devise a whole plan of action and just give you the final output. Lots of research questions there. How do we optimize this whole process? How do we control the quality? So we have lots of opportunities for our field to contribute. Want to mention also that large language models are black box models. It's very hard to interpret how they make their decisions. There is a field called mechanistic interpretability that is very successful these days. So it really means we need good human judgment, good research of how critical thinking can be implemented, and lots of opportunities for us to implement new methods. And so I really encourage you to look into this, because computer science field is sometimes lacking other ideas that we can bring. And then I want to mention also that those models consume so much electricity and water. There is so much research to be done into how to optimize the usage of the resources, how to provide data centers that are energy efficient, how to provide the ability to those big tech companies to still train those models, but in a sustainable manner. So for instance, Google and Microsoft have seen their water consumption increase by a factor of 20–30% every year. Same with electricity. So lots of people talk about how do we deal with that. And you can see recently they thinking about nuclear power as one opportunity.
Of course, there are also very significant privacy and IP implications of using large language models or generative AI that you should be aware of. Data privacy concerns, such as the use case that Leo mentioned of feeding an article, or even when you use client data, of course, you have to be aware of where it's going and what the rights are of whatever generative AI model you're going to associate with it. Intellectual property. There are still issues with bias and fairness like any other machine learning model. Regulations are changing. When can you use it? When you can't use it? What rights belong to who? And of course, ethical considerations, especially when you're using it for decision making. Transparency is very important, which is why it's important to understand what responsibility you're relegating to a model and what cannot be relegated. One of the most promising future directions of where these are headed are agentic systems, which were mentioned by Wei, which is often the results, when you think about how to create applications, integrating generative AI or integrating large language models, what often works is breaking it down into smaller pieces, even having the same model, but with different prompts, doing different parts of the work. And what's interesting, there are two very interesting, and of course for this you also need to have some coordination mechanism. So I encourage you to learn more about this, but I think two very interesting points is that often the coordination mechanism itself is an instance of a large language model, which takes care of coordination. And also a very important piece often is having a large language model instance that does validation of the outputs of other large language models. So Finally, I want to close with some research directions at the intersection of AI and ORMS. I think there are two primary directions. One is what can operations research, management science contribute to the development of large language models and generative AI, and the second is how far can we take these generative AI to actually help business decision makers make better solutions. Right. These are just some examples. You can read more in the online tutorial about how operations research management science can help large language models and generative AI with some of the core issues, robustness, IP of handling the issues around IP of data, effects on the labor market, how to maintain a vibrant and robust generative AI market, assuming that we see all the benefits that we hope we will be seeing from correct usage of generative AI. And the other direction is, so we showed how we can today already simplify the creation of optimization solutions, but what would be really, powerful is if we could give every decision maker for every problem the ability to create and to model and solve their problem using optimization behind the scenes. This is ongoing work done by Leo, myself, and some other colleagues. And we, of course, it's still very far along in the future. A very promising approach seems to be the agentic systems or the agentic paradigm. But this is sort of the vision of where we hope we'll be able to get, and if not, we'll still sure we'll be able to democratize a lot of work. So to summarize, we believe that generative AI and especially large language models already have and will continue to have a significant impact of work, including in our profession. We try to give a sense of the powerful technologies on which large language models are based. We try to help and to convince you that already today there are low-hanging fruit. We can already start using generative AI with analytics, with your analytics work, and also to give a brief sense, and hopefully we'll be able to touch more on this in the discussion time that we'll have remaining, on the exciting development and research directions of generative AI and the intersection of generative AI and operations research and management science. And what we'd like to end with is that due to everything that's happening, the speed at which this field is developing, we feel it's really critical to maintain AI literacy and keep up to date. But equally important is to make sure that we use it correctly and ethically, right? And perhaps the most critical skill is critical thinking and having validation built into the usage of generative AI. And with that, we'd like to end and open for questions and discussion.